Here we have a circuit and we have to determine the current in each branch of the wire. So first let's distinguish what each of the branches are by color coding them. Here's 1, 2, and 3. Now we can just label them as current 1, current 2, and current 3. Step 2, we have to fix a direction where current is flowing in each of these. This is just an arbitrary direction that you think might be happening. It does not have to be accurate. Next, we will define 2 loops since we have 3 wires. Whenever we're using Kirchhoff's loop rule, we should always define as many loops as the number of branches minus 1. Let's start out with the junction rule. So a junction is a point where 2 of the currents are going in and only 1 is coming out, or vice versa. So as you can see, current 1 plus current 2 equals current 3 here. And we can move all of the variables on one side by subtracting current 3 and equaling 0 on the other side. Next, we will define an augmented matrix. Some rules here are that the left side will have to be a square matrix where the dimension n equals the number of wires or branches that there are, and then the right side equals the battery or the volts that are added on, like the 4 volts or the 12 volts written right there. We can make this easier to understand by labeling each of these columns as current 1, 2, and 3. The rows will represent each of the functions that we create, and we will write the coefficient that is in front of each of the variables right under in 1. So with the junction rule, we have 1 I1 plus 1 I2 minus 1 I3. So we will write 1, 1, and negative 1. And since it equals 0, we will write 0 on the other side. Now let's do the same with Kirchhoff's loop rule functions. Let's start with this loop right here. First, we see that 12 volts is going in the same direction as the loop, so we'll add 12. And then there are 4 volts on the second current, but that's going in the opposite direction as the loop. As you can see, that the current is moving upwards, but the loop is down. So we will say negative 4. Now we look at all the resistors. On wire 1, we have 1 ohm resistor, and we have a 3 ohm resistor. So we will add them together because they're in series. And we get 3 plus 1 equals 4. So under the column of I1, we'll write 4. Now on wire 2, we have a 5 ohm resistor and a 1 ohm resistor, but they're both going in the opposite direction to a loop. So we will add them together because they're in series, but we will write them as negative 6 because they're in the opposite direction from the loop. And the third wire is not really considered in this loop, so we'll just write 0 because there are no resistors there technically. Now we'll move on to this loop. Here we have one battery, which is the 4 volts, and it's going in the same direction as the loop this time. So on the right side, we can write a positive 4. Now, resistors on the left, as we already saw, we have 6 ohms here, but this time they're in the same direction, so we'll write a positive 6. Then for wire 3, we only have one resistor, which is 8, which is going in the same direction, so we'll write a positive 8 under I3. And I already put a 0 for wire 1 because there is no wire 1 in this scenario. An augmented matrix is another way of writing this equation right here, which is saying that all these values are being multiplied by these 3 variables to get these 3 answers in 3 separate linear equations. This means that the answer to our augmented matrix will equal the value of these 3 variables in a vector form. And the way you solve for an augmented matrix is by row reduction to echelon form. So for that, we will use an online calculator, which is the Gauss-Jordan elimination calculator. On this site, we'll start by picking the dimension of our matrix, and then we will enter all the values as they are. You can use the fill empty cells with 0 button to make it faster. And when you press solve, you will be given the row-reduced echelon form of the matrix we entered. And these numbers as x1, x2, and x3 are the exact answers. So current 1 is 17/13, which is approximately 1.3. This is negative 6.13, which is approximately negative 0.46, and 11/13, which is approximately 0.846. And the negative doesn't mean that there's negative current. It just means that the direction that we chose for our second wire is supposed to be switched around. So if we fix it like this, our answer will be positive next time. And this just made solving with Kirchhoff's loop rule so much more easier. We can see that even more if we look at an example like this one. Let's label the wires once again in different colors based on the number of junctions there are. And we establish some direction that the current is flowing in that we think might be happening based on these 3 loops that we're going to draw here. Keep in mind we did 3 loops because later on we'll see that there are 2 junctions, and 3 plus 2 will give us 5, which is the number of wires that we've defined. Now let's look at the first junction. Here we can see that wire 1 is going in and 2 and 3 are coming out, so we can rearrange it to write this. And then at this junction we can see that 3 is going in and 4 and 5 are coming out. So 3 equals 4 plus 5, or we can move it to the other side to equal 0. These 2 are going to be our first 2 rows in our augmented matrix. So let's write that down. Let's label these as 1, 2, 3, 4, 5 so it's easier to understand. And we'll write down the coefficients. So that will be 1, -1, -1, and 0, 0, because these two are not in this equation. And for the second one, 0, 0, 1, -1, and -1. Now, since both of these equal 0, we'll write 0 on the right side of the matrix. Next, we look at all the loops and the individual wires. So let's start with the first loop we drew on wire 1. As you can see, there's one battery with 50 volts, so we will write 50 on the right side. Next, wire 1 has a 2 ohm resistor that is in the same direction as the loop, so we can write 2 ohms right there. And then wire 2 has another 4 ohm resistor in the same direction, so we can write 4 and fill in the rest with zeros. Now we look at loop 2, which has no battery, so we will write 0 on the right side. Then we have current 2, which is going in the opposite direction as the loop, so the resistor will have -4 ohms right under I2. Now we look at wire 4, which has another 4 ohm resistor, but this time it's going the same direction as the loop, so this will be a +4. And wire 3 has no resistors, so that's 0, and the other 2 wires aren't in this loop, so those are zeros. And finally, loop 3. Here we have a 20-volt battery that is going in the same direction as the loop, so that is a +20 on the right side. Then wire 5 has a 2 ohm resistor, which is in the same direction as the loop, so that is a +2 under 5. And then on wire 4, we have a 4 ohm resistor, which is going in the opposite direction, so that's a -4 under 4. And the others are 0 because they're not in this loop. Now that we have our huge 5x6 augmented matrix, we can use row reduction calculator online and enter all our values and then solve, and here are all our answers. Now we can write those out. So current 1 equals 20 amps, current 2 equals 5/2 amps or 2.5 amps, current 3 equals 35/2 amps or 16.5 amps, current 4 also equals 5/2 or 2.5 amps, and current 5 equals 15 amps. Now, just because the problem asks to solve for the power of each of these wires as well, we will do so by using the equation that power equals current squared times resistance. So power 1 equals current 1 squared times resistor 1, and then power 2 and 3, since they're the same, will equal the second current times resistance, and then power 4 will just equal whatever current 5 was times resistance 5. Oh, and I forgot to write the squared bit. It should be there.